SwayamPrabha. Digital India. Educated India.
So, today we will continue with our discussion on analysis of composite laminates which are piezoelectric patches. We started with the Galerkin technique, and then after the Galerkin technique to define these terms NXP, NYP, NZP that we did in the NSP that we did in the previous lecture. Now, just one thing to note, this expression is written considering for one patch. So, this should be doubled if I consider two patches, and here while writing the moment term we have considered two patches. At top and bottom, or I should say two identical patches, considering two patches which are identical and which are actuated in a antisymmetric way which can cause bending. Now, if I consider two patch here, these just quantities get doubled. All right. Now, then we looked into the Rayleigh technique, and in the Rayleigh technique this was the variational indicator that we wrote, and after putting all the expressions we wrote all the terms, in the inertia related terms, the internal virtual work terms and these external virtual work terms, everything in terms of our approximations. Now, it is time to finally arrive at the final equations. So, this is what we started with, and this we wrote, this we wrote, this we wrote, everything we wrote in terms of the approximations. So, finally, if we put all the approximations here, we get a term like this, and then we will get a term like this. And that is equal to 0. And again we know that these variations are independent and these are arbitrary variations. So, this entire quantity can be 0 only when I have this equal to 0 and this equal to 0. So, this gives us m plus n equations, and this gives us p equations, where m and n are the number of terms used to approximate our u 0 and v 0, and p is the number of term which is used to approximate our w. So, finally, the equation that would look like is this. Now, we will define these matrices. And in the right hand side we have F I. Similarly, here we have so this is our m plus n equations, and this is a system of p equations. Now, we have to define these matrices. MII is the integral over the surface of Ni transpose multiplied by MII into Ni, and then I have MIW, which is Ni MIW multiplied by NW, and then we have MWI is equal to NWT multiplied by MWI multiplied by Ni transpose d omega. Sorry, this is capital MW that we are talking about. Similarly, here we have MWW and we have NWT multiplied by MWW multiplied by NW d omega. Then comes the stiffness terms. So, we have KII, which is equal to BI transpose multiplied by A multiplied by BI d omega. Here we have KIW, which is equal to BI transpose multiplied by the B matrix multiplied by BW transpose. Then we have KWI, which is equal to BW transpose multiplied by the B matrix multiplied by the PI matrix. We have KWW, which is D matrix, which is BW matrix multiplied by D matrix multiplied by BW. And then if we so in the previous, so we have called it Fi, and then we have the Fi matrix, and which is Bi transpose multiplied by Np d omega plus omega Ni transpose multiplied by Qx Qy, and here we have Fw, which is BW transpose multiplied by MP d omega plus NW transpose multiplied by QZ. Now, so inside Fi, the force matrix, we have contribution from the NPs and the actual and the applied forces, and similarly you have in Fw you have contribution from MPs and the applied transverse forces. So, this is the entire formulation based on the Rayleigh-Ritz technique. So, here we can see that if the laminate is symmetric, then these two terms vanish, because in a symmetric laminate B matrix is 0 and this stiffness matrix and this stiffness matrix, they have B matrices. So, these two stiffness matrix does a stiffness coupling between the in plane components and the out of plane components. So, if our laminate is symmetric and if we know that the applied force is only along the xy direction, so we can separately just solve this. We can separately solve MII Qi double dot plus KII Qi is equal to Fi, because we know that because there is no coupling between the stiffness and in plane and out of plane terms, and the load is purely in plane. So, there is nothing going to be induced in the out of plane direction. In that case, we can solve the decoupled problem. Similarly, if the load is applied purely along the z direction, in that case also we can just solve MWW QW double dot plus KWW QW is equal to Fw. But if the laminate is not symmetric, in that case B matrix exists, and if the B matrix exists, then these coupling matrices KIW and KWI, they remain non-zero, and when they are non-zero, then even if my load is purely in plane, it will induce out of plane deformation, or if the load is purely out of plane, it will induce in plane deformation. In that case, the entire system has to be solved. Now, let us look into an example of pure in plane deformation. So, let us imagine that we have a composite laminate with piezoelectric patches, which looks like this when we view from top. So, this is our x direction, this is y direction. Along the x direction, the dimension is L, and along the y direction, the dimension is C. So, from here to here it is C by 2, from here to here it is C by 2. And then if we look at the same thing in the xz plane, it looks like this. We can assume that the piezo patch is distributed all over. Even if it is not distributed all over, our formulation can take care of that, that is not a problem. So, this is in the xz plane. So, this part is Tc, and for the sake of simplicity, let us assume that we have two identical piezoelectric patches of same thickness. So, this is our, these are our this is a piezo patch and this is composite laminate. And this is another piezo patch. And we have two identical piezo patches actuated symmetrically by voltage V. So, V top is equal to V bottom is equal to voltage V, and they are, because they are actuating symmetrically, it will induce only in plane deformation. And also, for the sake of simplicity, let us while assuming, let us imagine that our displacement deformation along y is not accounted for. So, along y. So, if that is the case, then accordingly let us make some approximations. So, assume u0, which should be as a function of x, y and y. Let us assume it to be only function of x, and then so there is no variation along the y direction. So, I would say that it is not just the deformation, it is a deformation variation along y direction. So, it is u0, and let us approximate only one term solution. So, there is no summation, we are approximating only one term solution. So, let us assume that to be phi u1 multiplied by q v1, and let us assume phi u1 to be x by L. Yes, it is x by L multiplied by q u1. Now, this satisfies the essential boundary conditions. So, at x equal to 0, u0 is 0, and again because there is no out of plane deformation, our laminate is symmetric. So, for pure in plane deformation, let us assume symmetric laminate. And the actuation is also such that it does not induce any moment, it induces only in plane forces. So, we can solve it as a purely axial problem. So, in that case, the stiffnesses like QIW and QWI can be neglected, and let us solve it as a static problem. Now, if that is the case, we solve only this QII multiplied by QI is equal to Fi. Now, we have k consists of only kii, and that is equal to our integral over the surface b I t multiplied by a multiplied by b I. Now, please understand that because we do not have other components of k's, we have only kii. So, we are just writing it as k, we are not specifying, and this becomes minus c by 2 c by 2, and we have to put the approximate I mean the B matrix in terms of the approximations. So, as per our approximation, epsilon 0 x, epsilon 0 y and epsilon 0 s, that is in terms of, if we write q u1, then it becomes phi u1 comma x, phi u1 comma y, phi there is no phi v1, and then we have phi u1 comma y. So, not only our variation of q variation of the u0 along y is 0, even our v is also 0. So, v 0 is 0, and then this B matrix, and then this entire thing is multiplied with QU1. So, we can say that our B matrix is essentially phi u1 comma x is 1 by L 0, and phi is not a function of y. So, it is also 0. So, B I is essentially 1 by L 0 0. So, this is 1 by L 0 0, A matrix remains as it is, and this is 1 by L 0 0, and this entire integration has to be evaluated from along y it is from minus C2 by C2 minus C by 2 to C by 2, and along x it is from 0 to L. Now, if we do the entire multiplication, this expression comes to be one by L square multiplied by A x x, and finally, after integrating, this comes to be A x x multiplied by C by L. So, k has only one component, so we can call it k 1 1 also, and similarly our F matrix, that is also going to have only one component. We will see that. And F matrix is going to be, as per our definition, it is B I transpose multiplied by the NP matrix. So, it is again 1 by L 0 0, and we have NPX and NPY and 0. And this expression after the integration comes to be zero to L NPX into L into C. Now, we can always solve, so and there is only one component, so we can call it F 1. So, we can always solve Q 1 Q U 1 multiplied by K 1 is equal to F 1, and that would give us Q U 1 as F 1 by K 1 1. So, once we get our Q U 1, we know the solution. Now, we will solve the same problem using the Galerkin technique. To solve it using Galerkin technique, let us make a different approximation, and the approximation is, again let us approximate that our variation of u 0 along y is not there and v 0 is not there. So, it is x by L minus half into x by L square, and v 0 is 0. So, there is no v 0, that is a much simplified approximation. Now, when we solve it using the Galerkin technique, the phi is this okay, so this has to be multiplied with q u1 and which we call phi u1 multiplied by q u1. So, this phi u1 is going to be differentiated twice. So, that is why we had to use a different approximation functions, and it satisfies both the geometric and force boundary condition. So, our geometric boundary condition is that this part is clamped. So, u0 is 0 here, and the force boundary condition is at the free end there is no force. So, u0 is equal to 0 at x is equal to 0 and del u0 by del x is equal to 0 at x equal to L, and this approximation satisfies those conditions. Now, we know that we already discussed the governing equations, and we know that according to that the differential equation is this, and then we define a error function. The error function that we define is, or it is a residue. So, the residue that we define is minus of del p x by del x. Now, what we do is that we multiply this residue by the basis functions one by one. In that case, we have only one. So, we just multiply with phi u1 and integrate it over the surface and make the residue 0, and that gives us the desired equation, solving which we can find out q u1. So, we have phi u1 multiplied by epsilon d omega integrated over the omega is 0, and which also tells us that phi u1 multiplied by a x x multiplied by del 2 phi u1 by del x 2 multiplied by q u1 minus del f p x by del x dx, it is d omega, and that is equal to 0. Now, here we can see that this phi u had to be differentiated twice. So, that is why we had to make this approximation. The previous approximation that we made while solving the Galerkin while solving using the Rayleigh's technique does not work here. And then finally, after evaluating all these integrations, and we know that this d omega is equal to 0 to L minus c by 2 to c by 2 dy dx. So, after evaluating these integrals, finally q u1 comes to be 3 L n p x divided by 2 x a x x. Now, here f p x is basically our n p x, the first term in that f p vector. So, that is the solution that is obtained using the Galerkin technique. So, we have solved this in plane problem using both the Galerkin technique and the Rayleigh's technique. In the next class, we will solve an out of plane problem where there will be pure bending. So, with that let us conclude this lecture. Thank you.